Sound check one. Okay, good morning everybody. We're going to go ahead and get started. We're going to look at practice test 2. Remember, you have access to this printout. It's in your OneNote folder, which is linked to your Canvas. Please let me know if, as we go, you have any questions, or if there are particular items that you'd like to see worked. But I'm going to just start by going through one at a time and try to focus our time on the basic concepts that I think are the most important for you to be successful on this test and for the rest of the class. Just going to make this screen a little bigger here. Oops. Okay, so item number 1 is definitely a skill that you need to have, which is differentiating a function that is given to you in a form where you have a little bit of, if you do just a little bit of algebra, it might actually make your life a little easier. But the answer that is shown here might not be how your answer turns out. So you'll have to be able to compare your answer at the end as well. So let's take a look. So when you look at this function and you're asked to find the derivative, you want to look at the form of the function. Notice that it's a quotient. So what that means is you cannot just take the derivative of the top and the derivative of the bottom. You would have to apply the quotient rule you would have to apply the quotient rule if you leave it in this format. However, how about instead of just going right ahead and applying the quotient rule, which can get a little bit messy, what if we simplified it algebraically before we try that? So what I would recommend instead is that we actually divide each term by the x in the denominator. So in other words, this is really y equals x cubed over x minus 3x squared over x plus 9 over x. And simplifying, that means that y is equal to x squared minus 3x plus, we could even write this 9 over x as 9x to the negative 1 power. So now, instead of having a big quotient, we have individual terms, which are easier to differentiate. So we can find y prime by taking the derivative of each term. So the derivative of x squared would be, would apply the power rule. And remember, when you take the derivative of x to the n power, you get n times x to the n minus 1. So in this case, we would bring the power up front. We get 2x to the 2 minus 1 is 1 power, the first power. Minus, here the 3x is to the x is to the first power. The 3 stays the same. And then if we differentiate using the power rule, you can think of it as times 1x to the 0. But really, remember the derivative, you can also just remember the derivative of x is always just 1, because anything to the 0 power is 1. All right, another way you could think about that particular term is if you had the function y equals 3x, that would be a line with a slope of 3. So the derivative of 3x is just 3, because remember, derivatives is just slope. Okay, and now on this last one, we have 9 times x to the negative 1. The 9, the coefficient stays the same, times, we're going to bring the power out front, that's negative 1, and subtract 1 from it. Negative 1 minus 1 is negative 2. Okay. All right, so now we're going to just simplify a bit. So we have 2x minus 3 plus, or actually minus, 9x to the negative 2. All right, but notice that, well, first of all, we don't like leaving a negative exponent in our answer. That's not the form that we like. So let's write that as 2x minus 3 minus 9 over x squared. All right, this is a perfectly valid solution for the derivative. And so, but you might notice that it doesn't look like the answer that's provided here on the worksheet. Can anyone tell me, what could you do to either one of these, either the answer they provided or the answer that I wrote down, to make it look like the other one? Maybe Trina or Annalise, do you have any idea how we could see that these two expressions are really equal to each other? So yeah, it has to do with the x squared. And you're right, if we looked at the expression that we were given by my math lab as the solution over here, you could divide each part by the x squared, and you would see it's the same answer that we got over here. Look, 2x cubed divided by x squared would be 2x. 3x negative 3x squared divided by x squared would be negative 3, and negative 9 divided by x squared is negative 9 over x squared. So this really turns out to be exactly the same answer. Or if you wanted to look at my solution, you could get a common denominator and perform the subtraction over here, and you'd get the answer that they show. Okay. All right, well, again, if you're feeling a little bit lost, just make sure that as you're watching what I'm doing, that you're thinking about each step. And if there's a particular step that doesn't make sense to you, you need to feel free to interrupt me, okay? Or tell me to go back to the previous problem, or whatever the case may be. All right, so you see how in problem number 1, we turned our expression from a division problem, a function that has division of a large polynomial in it, into a function that looks just like a regular old polynomial, terms that are separated by plus or minus only, not by division. We would like to do that whenever we can, because that power rule is pretty easy to use compared to a lot of the other rules. All right, so again, when you look at number 2, it doesn't have a big quotient in it, but it has a square root, and there isn't a derivative rule for a square root. So whenever you see a square root, always rewrite it as an exponent. And what is the square root written as an exponent? What power is the same as a square root? Does anybody know? You're on the right track. It has to do with the 2 because it's 20 times the square root of t. The index is 2. But remember, the square root is not the same as t squared. What it's the same as is t to the 1/2 power. So whenever you have a square root, you want to rewrite it as a 1/2 power. Whenever you have a cube root, you want to rewrite it as a 1/3 power, and so on. So what we're going to do on this problem is we're going to say, okay, g of t is equal to 20t to the 1/2 power. That way we can use the power rule. And remember again what the power rule said is if you take the derivative of x to the n power, you're going to get n times x to the n minus 1 power. So you bring the power out front and subtract 1 from it. Any coefficients that are in front of the variable are just going to tag along. So your first derivative will be 20 times, then we're going to bring the 1/2 out front, and then we're going to multiply by, and what's 1/2 minus 1? I'm going to write that step out. So we're going to have g prime of t is equal to 20 times 1/2 is 10. And then we have t to the what power? What's 1/2 minus 1? Good, negative 1/2. So now this is the derivative, but it's just not in a form that we like to leave it in. So first of all, we don't like to leave negatives in our exponents. So one way you could write this derivative would be 10 over t to the 1/2 power. However, since we did start with a radical notation instead of an exponent notation, you might want to put it back like they did into the form 10 over the square root of t. Okay, Let me know if there's any questions about that one. Now there is a delay between when I speak and when you hear me, so I'm going to continue moving along, but you really shouldn't be shy about asking me to scroll back up, okay? All right, here we go. Okay, this one says find an equation of the tangent line to the given curve at x equals a. Use a graphing utility to graph the curve and the tangent line on the same set of axes. And the function that they're giving us is y equals 4 plus 3x plus 2x times e to the x. So before we work this exercise, I just want to work an example similar to finding the derivative of this guy here. So I'm going to back up and we're going to find the derivative of, actually we'll do a couple of examples. Part A, we're going to do the derivative of f of x equals, and we're going to do e to the x. All right, so this is completely different from finding the derivative of, say, x squared or x cubed, where the x is in the base. Here the x is in the exponent. The variable is in the exponent. What that means is that the power rule does not apply. In other words, you can't just bring the x out front and subtract 1 from it. It doesn't work that way. Okay, so what do we do instead? Well, there's a whole list of derivative rules in your textbook, and one of them says that the derivative of e to the x turns out to be e to the x, which is actually kind of an interesting thing because remember, a derivative is the slope of the function at any particular point. So this function is special because its function value is the same as its slope. So the y value at every point is the same as its slope at every point, which is kind of interesting. But it also makes our job of finding the derivative easier because when we have derivative of e to the x, we just say e to the x. All right, and part B, we're going to find the derivative of f of x equals x squared times e to the x. Okay, so in this case, we have a product of two separate functions. In other words, something with an x times something with an x. And unfortunately, we cannot just take the derivative of each part. The slope of the function does not turn out to be the slope of each part multiplied together. I wish it did, but it doesn't. So when you see that you have something with an x times something with an x, you have to use yet another rule for derivatives, which is called the product rule. And what the product rule says is if you're taking the derivative of the product of two functions, f of x times g of x, or whatever their names are, doesn't matter, you're going to have the first function times the derivative of the second plus the second function times the derivative of the first. In fact, what a lot of people do when they're writing down the formulas, they actually use capital F and capital S to represent first function and second function. So capital F of x times capital S of x, first and second. And then, so first function, first function times the derivative of the second plus the second function times the derivative of the first. Okay? All right. So in our problem, the x squared is what I'm referring to when I say the first function, and e to the x is the second function. So let's write that down. Capital F of x is referring to x squared, that's the first function, and e to the x is the second function. Okay, and so we're going to just use this rule. So in the process of using this rule, we're going to need the derivative of f and the derivative of x. So before we start trying to plug into the rule, let's go ahead and write down those derivatives. So f prime of x would be, well, the derivative of x squared is 2, bring the power up front, 2x to the subtract 1 from the exponent, you get 1, but you don't have to write it. And s prime of x, the derivative of e to the x, is just e to the x. So to find my derivative of little f, I need capital F times the derivative of s plus s, the second function, times the derivative of the first function, capital F. So let's just plug in these values here. So capital F of x is x squared. Derivative of the second function, s, is e to the x, plus s of x is e to the x, times f prime of x is 2x. Okay, now oftentimes we will, it will be helpful to take, this is the derivative, but a lot of times it's helpful to have it in factored form. So I just want to point out that you could leave your answer in factored form. Notice these two terms have something in common. They have an e to the x in common and an x as well. So I'm going to factor out x e to the x, and let's see what's left behind here. We would have an x plus, and then we would have just a 2. So x e to the x times x plus 2. Okay, all right, so I wanted to work that problem before we do the next one. Number 3. Because it has, part of this function involves the product rule as well, it has a similar situation here. It's in the context of them asking us to find the equation of a tangent line. So when you're finding the equation of a tangent line, you have to remember that to find the equation of any line, we need slope, right? We need the slope and a point. So when we find the equation of a tangent line, the slope is actually the derivative evaluated at whatever point we're looking at. In this case, the x value a, which is 0. So we're going to have to do several things. First, we're going to have to find y prime. Then we're going to have to plug in 0 to get the slope. And then thirdly, we're going to have to find the y value at 0. So we're going to have to plug in 0. In step 2, we're plugging in x equals 0 to the derivative to get the slope. In step 3, we're also going to have to plug in x equals 0 to the original equation y, the original function, just to get the y value of the point. And then step 4, we're going to use the point and the slope to get the equation of the line. So there's a lot to do here. Okay, so let's, I might need to slide over and make myself some space here. So the function is y equals 4 plus 3x plus 2x e to the x. Okay, so y equals 4 plus 2x, oh, was it 2x? 3x. 4 plus 3x plus 2x times e to the x. Okay, so we're going to do step 1. We're going to find y prime. Slide that over a little bit. Okay, step one, we're going to find y prime. So when the function you have, see how it has everything's being added together except this last term, which is something with an x times something with an x. So anything that's being added together, we can just take the derivative separately. So for example here, for y prime equals the derivative of 4, any constant, is just 0, plus the derivative of 3x. Anytime you have a number times just x, that's just going to be the number, the coefficient, which is 3, plus, and then we have something a little more challenging. We have something with an x times something with an x, which means that we have to use, just for this term, the product rule. Okay? So to take the derivative of this term using the product rule, we're going to say the first function, capital F of x, is going to be the 2x. Let me do this in a different color here. All right, so we'll think of 2x as the first function, and we'll think of e to the x as the second function. So if f of x is 2x, then its derivative would be what? What's the derivative of 2x? Oops. Very good. It is 2. Good job. All right, so the derivative of 2x is 2. Now our second function, s of x, is going to be that e to the x, and the derivative of e to the x is the easiest function to take the derivative of. It's the same function, e to the x. Okay, so remember the product rule says that the derivative is going to be the first function times derivative of the second plus the second function times derivative of the first. So when we're finding the derivative of 2x e to the x, we're going to have the first function, which is 2x, times the derivative of the second, which is e to the x, plus we're going to have the second function, e to the x, times the derivative of the first function, which is just going to be 2. All right, so our y prime is this string of terms here. Let's simplify it a little bit. So y prime is equal to 3 plus 2x e to the x plus 2e to the x. Okay, so that was just step 1, finding the derivative. So we've done step 1. Let's check it off here. All right, next, step 2, we're going to plug in x equals 0 to the derivative that we just found to find our slope. All that a derivative is a formula for slope. And in fact, calculus could have been called slope because it's all about slopes in one form or another. So we're going to plug in to y prime. We're going to plug in, and you can use this little bar to indicate that x equals 0. That's what we were given. You don't just always plug in x equals 0. It depends on what point they're asking you to find the slope at. So we're going to have 3 plus 2 times 0 times e to the 0 plus 2 times e to the 0. Okay, so the slope of the function at x equals 0 is going to be 3 plus, now this is just going to be 0. E to the 0 is 1, so this is going to be 2. So it's 3 plus 2, which is equal to 5. So our slope is equal to 5. All right, so that was step 2, plugging in the x value of the point we're interested in to find the slope at that point. All right, but when you find the equation of a tangent line, in fact, when you find the equation of any line, you not only need the slope, but you also need a point to make it work. We know that the x-coordinate of the point we're interested in is 0, but we also need the y-coordinate. But that's okay because we have the original function to plug into. So we are going to plug into y equals 4 plus 3x plus 2x e to the x. And we're going to plug 0 into that. Y evaluated at x equals 0 is 4 plus 3 times 0 plus 2 times 0 times e to the 0. These two are going to both turn into zeros, so we have that the y-coordinate that we're looking for that goes with 0 is just going to be 4. Okay, so we just did step 3. We found the y-coordinate. Sometimes step 3 is done for you in the problem. They'll give you both coordinates, but not always. Okay, and then use the point and the slope to get the equation of the line. Now, at this step, since this is calculus, and you guys have taken a lot of math classes prior to this and done a lot of algebra, you may have learned different procedures for writing the equation of a line. For example, you might have learned to use the point slope form of the line, which looks like y minus y1 equals m times x minus x1, and you would plug in 0, 4, and 5, or you might have learned to plug into y equals mx plus b and solve for b if the y-intercept is not given to you. So depending on the problem that you're working, you might have to, and depending on your background, you might choose to approach this in a different way. But in this particular case, the problem is actually easier because this happens to be a y-intercept. And the reason I know it's a y-intercept is because the x-coordinate is 0. So whenever that happens, you definitely want to use y equals mx plus b because you know b and you know m, right? So we can just say that the equation of the line is going to be y equals 5x plus 4. And we're done with that part of the question anyway. We found the equation of the tangent line. Okay, so be sure to let me know if you have any questions about any steps so far. I'm going to zoom out for a second here. Okay, there is another part of this question that asks you to graph the function and its tangent line. Let me, hold on, there we go. Okay, now first of all, let's use process of elimination, because you don't have graphing calculators. So for part A, option A, this is not a tangent line. Generally speaking, tangent lines don't cut through the function. They kind of glance off the function like that. Also, our tangent line equation that we got was y equals 5x plus 4. which has a positive slope, and the tangent line pictured here doesn't. So it's definitely not A. B looks like a possibility to me because it is a tangent line. It's actually just touching the function in one point, and also it has a positive slope. So let's keep that one as a possibility. And then C looks like it has a horizontal tangent line that would have a slope of 0, so that's not going to work. And then D has a negative slope, so you know it's not going to be right. So it must be that B is the picture of the function. And if that weren't enough, I would also plot a few points on the function just to see if it matches up with the equation of the function we were given, which was y equals 4 plus 3x plus 2x e to the x. Just plot some points. Okay, so that's how you would work that one. Okay, the next problem, number 4, is a problem for which involves a variation on how to find derivatives. I think that no, yeah, let's do this one first. Okay, so to work problem number 4, notice that we have something with an x raised to a power of something with an x, and you cannot use the power rule whenever there is an x in the base of the exponent. No, yeah, you can't use the power rule whenever there's an x in the exponent. Cannot use power rule. Power rule only works when the power is a number. Okay, so we saw one case of that was when we saw that the derivative of e to the x was equal to e to the x. We have a rule to help us with that particular function, but this isn't that situation either. In fact, this is more complicated because the derivative of e to the x, the e is a number, it's 2.7 something. Here we have a variable in the base. So usually what we do when we have a situation like this one is we take the derivative using something called logarithmic differentiation. And we are going to do that now. So what you do for logarithmic differentiation, so let me put a note here, use logarithmic differentiation. Is you take the natural log of both sides of the function. So you say the natural log of y must be equal to the natural log of x to the secant of x power. And the reason why you do that is because, remember, there's a rule for logarithms called the power rule. Power rule of logarithms, not the power rule of differentiation. The power rule of logarithms says that if you take the natural log of x to the p power, that's p times the natural log of x. You use that in college algebra and pre-calculus to solve equations. We're going to use it here to get that expression with the x out of the exponent, since we don't have a derivative rule for that expression. So what we're going to do is say the natural log of y equals, bring the power out front, we have secant x times the natural log of x. Okay, the next thing that we're going to do is take the derivative of both sides of the expression, keeping in mind that what we really want to find is y prime, the derivative. But what you'll see is that in the process of taking the derivative of both sides, we'll be able to isolate y prime. So let's take the derivative of both sides. Okay, so the derivative of the natural log of y, okay, this is a rule that we should know. To take the derivative of a natural log, d dx of the natural log of x would be 1 over x. But in this case, the variable doesn't match up. So what you do when you have the derivative with respect to x, but you're taking the derivative of a function of y, is you say it's going to be 1 over y, just like it was 1 over x, except since it wasn't a y, you multiply by y prime. So you get 1 over y times y prime equals, and then over here we have a product of two things with an x. So there's a first function and a second function. So once again, we have a capital F of x and a capital S of x. So you're going to have your first function, which is secant of x, and you're going to have your second function, S of x equals natural log of x. Now the derivative is going to be the first times the derivative of the second plus the second times the derivative of the first. So we're going to need to take the derivative of each part. So what's the rule for the derivative? There's a rule for the derivative of each trig function. Does anyone know the rule for the derivative of the secant? I'm going to, let's see, show you. You can find it in your textbook, but you can pretty much just Google derivative rules and get a nice list that you could print out and keep with you as you're studying. You need to know them for the test, but to get to that point, keep the list with you, and then as you're studying, write it each time. So let me grab one from the internet just to show you how accessible they are. List of derivative rules. Okay, so here, for example, from the website called Paul's Online Notes, I think it's called, there's a PDF with a whole list of derivative rules and different facts about derivatives that you should know. I'll go ahead and print this one into our OneNote real quick so that you have it. Okay. Okay, so that's going to be right in the same folder with our live chat there. So anyway, let's look on here for our derivative of secant. So right here we have the derivative of secant of x equals secant x tangent x. Okay, so that is something you should memorize. Oops. So remember, what we were working on is, in the process of solving this problem, we needed to find the derivative of the secant x as part of our product rule. So we're going to say f prime of x equals secant x tangent x. Okay, and then we need the derivative of the natural log. Remember, I just mentioned the derivative of the natural log is 1 over x, but I just want to show you on this derivative sheet, it says that right here, derivative of the natural log of x is 1 over x. Okay, so we're going to say s prime of x equals 1 over x. All right, so we're going to do first times derivative of the second plus the second times derivative of the first. Okay, so that's going to be secant of x times natural log of, 1 over x plus the natural log of x times, and then we're going to have secant x tangent x. I'm running out of room here. Let me move this. Okay. All right, so remember, this is almost what we want. This is 1 over y times y prime, but what we really want is just y prime. So I'm going to multiply both sides by y to get the y prime by itself, and we get y prime equals secant of x over x plus natural log of x secant x tangent x. All of that multiplied by y. Now, we don't like having y's in our derivatives, generally speaking, but remember, we know what y was equal to. Y was equal to x to the secant of x power. So let's write this as y prime equals secant x over x plus natural log of x secant x tangent x times x to the secant x power. Okay, so that's our derivative, and we had to use the logarithmic differentiation in order to get it. And again, the reason why I did that is because we had something with an x raised to a power of something with an x. All right, now let's go back and look at what we're supposed to be finding again. All right, so for this problem, we're being asked to find an equation of the line tangent to the following equation at the point x equals 1. We did the first step. Remember, step 1 is to find the derivative. Step 2 was to plug the x equals 1 into the derivative to find the slope. And then step 3 is to plug it into the original function to find the y value for the original function. So we've done step 1, we found the slope of or the formula for slope, and now we're going to plug in x equals 1 into our derivative, y prime. We're going to evaluate it at x equals, not 0, 1 this time. That information was given to us in the problem that we wanted evaluated at 1. Okay, so we're going to plug that in for x. So we're going to have y prime evaluated at x equals 1 is going to be secant of 1 divided by 1, which is just secant of 1, plus, now we have natural log of 1 there. The natural log of 1 is going to be 0, because what that's really saying is what power do you raise e to get 1? And you raise it to the 0 power. So that whole term is going to turn into a 0. And then we're going to have 1 to the power of secant of 1. But 1 to any power is just 1. So 1 times secant of 1 is just going to be secant of 1. Now I'm just writing secant of 1 and not evaluating it because it doesn't, 1 is not a special angle. So it's not going to turn out nicely. So we just leave it as secant of 1. So your slope is actually equal to secant of 1. All right, so we have done two steps. We have found the derivative and we have found the slope by plugging in. Now we need to plug into the original function in order to find just the y coordinate of the function. The x coordinate is 1. Our original function is x to the power of secant x. So to evaluate y at x equals 1, we get 1 to the secant of 1 power, which again, 1 to any power is just 1, so that's just going to be 1. So the point that we're interested in is the point 1, 1. So now using our slope, secant 1, and our point that we were given, we have to write the equation of the line. So here again, you have, this time unfortunately, we were not given the y-intercept of the line. So we can't just say, oh, y equals mx plus b, m is secant of 1, and b is 1. That would not be correct, because that would only work if we had a y-intercept. But we still can use y equals mx plus b, and here's how we can do it. We have the point xy, and we have m, so we plug in and find b. So we're going to have 1 equals, then we're going to have secant of 1 times 1 plus b. Secant of 1 times 1 is just secant of 1, so if you subtract that, we get our b is equal to 1 minus secant of 1. So we have our m and we have our b. So now we can write the equation of the line. Right, so y is equal to secant of 1 times x plus b, which is 1 minus secant 1. Okay, and so that's what you can see, that's what they got up here in the solution. All right, so I know that was a long problem. Anybody have any questions so far? This was item number 4 on your review. The parentheses I put around the 1 minus secant of 1, I just did that to kind of emphasize that that was like our b. But by order of operations, it doesn't matter if you include the parentheses or if you don't. The answer would be the same. Thank you for asking, Annalise. I'm sure other people will wonder the same thing. Okay, anything else? All right, so let's do number 5. Number 5 is about implicit differentiation. And I think I'm gonna move this down a bit to make some room for number 5 here. Okay. All right, so for number 5, we are looking at, I'm gonna rewrite it here. We're looking at the equation 5x to the 5th plus 2y to the 5th equals 7xy. And this equation is a relation. It gives a relationship between the x and the y value. What we would like to find is dy dx, the change in y with respect to x, the derivative of y with respect to x. But we normally do that. When we normally do that, we have y equals something. So when we have a situation like this where we would really not be able to solve for y to get y equals something, then another alternative is to use implicit differentiation to find dy dx while the equation is still written like this. And the way that we do that is just to take the derivative of both sides with respect to x. Before we do that, though, before we find dy dx, I just want to explain again that when you take the derivative of something that's not the same variable that you're given, then what you do is basically apply the chain rule, which is to say that you just go ahead and you take the derivative of the function as it stands. So, for example, here it's a power rule. You'd bring the power out front, subtract 1 from it, so you get 5y to the 4th. But since that wasn't an x, since it was a y, we multiply times the derivative of y. So you would write 5y to the 4th dy dx. So really you just slap in a little y prime or dy dx after the derivative whenever the two variables don't match up. Okay, so if it had been, for example, ddr of s squared minus 3s, you would do the same thing. You would pretend like you're taking the derivative with respect to s, so you'd write 2s minus 3. But then, since that wasn't an s, you would multiply times the derivative of s with respect to r. Or write s prime if you prefer. Okay? All right, so with that in mind, we're going to come over here and we're going to find where did the 4 come from on the power of y? Because remember, the power rule says that you take the power out front and subtract 1 from it. So 4 was 5 minus 1. Okay. All right. So I'm going to zoom in a little bit. All right, we're going to find dy dx here. And again, we can't solve for y, so instead, we're going to use implicit differentiation. Which means just taking the derivative with respect to x, y with respect to x, because we're trying to find dy dx. So when I say with respect to, I'm talking about the variable in the denominator. So d dx of all of that stuff. The derivative with respect to x of whatever's in the equation. So 5x to the 5th plus 2y to the 5th. And on the right, we're taking the derivative of 7xy. Okay, so when we take the derivative of a sum, we can just, you have a little glitch. Yeah, sometimes that happens. Actually, the stream health that I'm having on my end is actually pretty good today. Sometimes I have bad days, but luckily, knock on wood, so far today's been good. But yeah, if you miss a second or two, don't hesitate to ask me. But it's always a little behind, though. I mean, there's a definite delay between when I speak and when you hear me, and when you respond and when I hear you. So, all right. So anyway, the derivative of 5x to the 5th, you're going to have to apply the power rule again. So the 5 stays the same. You bring the other 5 out front and subtract 1 from it. So you get 5 times 5x to the 4th. Now, notice the variables matched up here, the x and the x. So you don't have to do anything else. That's it. You're done. Plus, but now when we take the derivative of 2y to the 5th, the variable doesn't match up with the dx, which is okay. But that means you apply the power rule and then you just add in a little dy dx at the end. So we're going to have 2 times, bring the 5 out front, subtract 1 from it, times dy dx. Okay, so that's how you differentiate the left side. We'll simplify in a minute. And then on the right, what operation do you see there? This is multiplication, right? It's not addition. So we can't just differentiate 7x and differentiate y and multiply them together. That doesn't work that way. We have to use the product rule. So for the product rule, again, you have the first function, f of x is 7x. And you have the second function is going to be y. And so the derivative of f with respect to x is going to be 7. And the derivative of y with respect to x is dy dx. So I'm going to use my product rule. I'm going to say first times the derivative of the second plus the second times the derivative. I'm sorry, I just wrote it wrong. Hold on. Plus the second times the derivative of the first. And that's going to be 7x times the derivative of the second function was just dy dx plus s, which is y, times the derivative of the first, which is 7. Okay? All right, so we have differentiated on both sides. Keeping in mind our goal is to find dy dx, right? So we're going to simplify a bit, and then we're going to try to get dy dx by itself so we can see what it's equal to. So we have 25x to the fourth plus, then we have 10y to the fourth dy dx equals, and then we have 7x dy dx plus 7y. All right, so this, think of dy dx as just another variable. This is just like when you're solving a formula for one of the variables in the formula. Whatever terms have the variable you're looking for, you want to get that to one side of the equation, and everything else you want to move to the other side. So, to solve for dy dx, we're going to move the terms with dy dx to one side. Let's just go ahead and move to the left, and the other terms to the right. So that means that we will have 10y to the fourth dy dx minus 7x dy dx equals, and then we'll have 7y minus 25x to the fourth. All right, why do we do that? Well, now that we have them, the dy dx's both on one side, to get them to appear as just one dy dx, all we have to do is to factor out the dy dx. And what's left behind is 10y to the fourth minus 7x. Okay, so what can we do next to get dy dx completely by itself? The last step is always just to divide, right? We can divide both sides by what's in the brackets. So we're going to have dy dx equals, then we're going to have 7y minus 25x to the fourth over 10y to the fourth minus 7x. Now you might notice this looks a little weird, right? Normally when we find the derivative of y with respect to x, we have all x's in our expression. But remember that we couldn't get the y out, so it's normal to see the y appear in that derivative when we use implicit differentiation. Let's see, what else did they ask us to do in this problem? That's it. Okay, and here's their answer. Oops. Theirs is reversed from mine in the sense that it looks like 25x to the fourth minus 7y over 7x minus 10y to the fourth. Those are equivalent, right? Because if you multiply the top and the bottom each by -1, which doesn't change the value because -1 divided by -1 is 1, distribute the negative, you would get the version that I have. It was just when they were solving their equation for dy dx, they probably moved the dy dx's to the right instead of the left and changes the signs. But it's all equivalent. Okay, any questions about that one? No, you can enter the answer either way and it should be marked correct. My math lab should recognize that those are equivalent. Okay, we probably have time for one more question, but I'm just trying to look to see what we haven't discussed. We discussed logarithmic differentiation, implicit differentiation, product rule, finding the equation of a tangent line. Some of the questions are multiple choice and some of the questions are not. So if it's multiple choice, you're going to have to recognize, like if you solve it one way, you're going to have to recognize that the answer given was, equivalent to your own answer. If it's not multiple choice and you enter the answer one way, the system should recognize it. And by the way, whenever you take a test in my class, if you put in an answer and it's equivalent to the answer that was expected, but for some reason the system doesn't recognize it, or perhaps maybe you made a small typographical error and it was marked wrong, but I can tell looking at it that you really should have gotten at least most of the credit. That is definitely something that I highly, highly encourage you to bring to my attention so that I can manually update your score, because the computer systems aren't perfect. But yeah, a lot of the questions on the test are multiple choice, but not all of them. I try to include some of each. Okay, we haven't done a quotient rule problem, and I want to make sure everybody's good with that. And we also haven't done just a regular old chain rule problem, so I would like to make sure everyone's good with that as well. So let's go ahead and try to finish number 12 and 13 before I have to log off at 11:30. All right, so let's start with number 12. All right, so even if I didn't tell you in the instructions to use the quotient rule, you should know when you're looking at a function that has something with an x divided by something with an x, or maybe even something with a variable divided by something else with a variable, you're going to use the quotient rule. Okay, so what does the quotient rule say? And this is something you should be very comfortable with. There was a question about the practice test. When you do the test, then the homework, will those scores be added out? So am I understanding your question that you're wondering if you do the homework after you take the test, will you still get credit for the homework? The answer is yes, but of course it's better to do the homework prior to the test because it helps you to prepare. Okay, so also if you do the homework past the due date, then there's might be a penalty, if I'm remembering the settings correctly. So watch out for that. Okay, so the quotient rule says that if you have a function y equal to a top function over a bottom function, the homework that comes up after you take the practice test, that one homework assignment for after the practice test is what it is whatever you get right on the practice test gets marked done on that homework assignment. So yeah, so it's only the questions you miss on the practice test that you get more practice with on that homework. And it does count as a homework assignment. And it has the same settings as the other homework assignment that if you do it by the due date, then you get full credit. And but you can submit it after you take the test and you will still get credit. I hope I'm answering your question. Okay, so the quotient rule says that it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Be careful, unlike the product rule where it's an addition in the middle, the quotient rule has subtraction, so the order matters. If you get the order backwards, you're going to get the opposite of the function you're looking for. So in this case, the top function t of x is x minus 1, and the bottom function b of x is 2x minus 3. So the derivative of the top is going to be the derivative of x minus 1, which is going to be 1 minus 0, or 1. And then the derivative of the bottom, b prime, is going to be the derivative of 2x minus 3, which is going to be 2 minus 0, so 2. So if we take the derivative of x minus 1 over 2x minus 3, it's going to be the bottom, which is 2x minus 3, times the derivative of the top, which was 1, minus the top, minus the top, which is x minus 1, times the derivative of the bottom, which is 2, all over the bottom squared, which is 2x minus 3 quantity squared. And then that is going to need to be simplified a bit. We have 2x minus 3 times 1 is 2x minus 3. Distributing the negative and the 2, we have minus 2x plus 2 over 2x minus 3 squared. And now the 2x's cancel out. Negative 3 plus 2 is negative 1, so we get negative 1 over 2x minus 3 squared. Okay, so that's number 12. All right, and I think I'm going to have to stop there because I don't think 5 minutes is going to be enough to get through number 13. I just want to remind everyone that this printout is here in your OneNote, and you have the opportunity to if you take your test up to 2 times, but you should prepare as much as possible for that first time, and then if you don't achieve the score that your goal score, What you should do is go back through and look at what you missed. Maybe reach out to me for assistance with the problems, the types of problems that you missed, and then you can retake the test. If you retake it by the deadline, then you would get full credit. And then if you retake it after the deadline, then you have a 10% deduction. That's just to encourage you to stay on track and get everything done by the deadline so that you don't fall behind in the class. I really want you to be successful, and I'm here to help you, so please don't be shy about contacting me. My contact information is in the syllabus. Oh, you're welcome, Annalise. Oh, when is test 2 available? That's a good question. Let me take a peek here. Test 2 opens up on, let me make sure I'm looking at the right place. Yes, looks like September 25th. So in 4 days, it's going to open up, and it'll be open until October 1st. Okay. All right, and if you found this, whether you're watching it live or perhaps somebody's watching this, the recorded version of this, which will be posted in the OneNote, if you find it helpful, please remember to give it a thumbs up, give it a like. That just helps other students to find the video. Okay, and don't be a stranger. I know this is an online class, and it does make communicating a little bit more of a challenge. But just like in a face-to-face class, when you need help, that's not the time to give up. That's the time to get stubborn and reach out and be the squeaky wheel and get some help. Okay? All right, guys, you have a good weekend. Good luck with all your homework. Send me those Ask My Instructor questions, and study hard. Okay? Bye-bye.